Mutual inductance. Now let's say that there are two circuits nearby. So we have coil 1 and coil 2 that are close to each other. The magnetic flux through the area enclosed by one circuit can vary in time due to time-varying currents in a nearby circuit. This is called mutual induction. So if we have the flux through this coil varying due to a time-varying current on the first coil, which creates a change in the magnetic field created by this coil, this will change the magnetic flux going through coil 2 and it will cause mutual inductance. Now, let's first set I2 to 0 so that there is no current flowing through the second coil. And the current in coil 1 sets up a magnetic field, and some of these magnetic field lines will pass through coil 2. I1 in coil 1, in the first coil, with N1 turns, creates a magnetic field B1. So let's say this is the magnetic field created by this coil, and some of these field lines pass through coil 2, and I1 of t, if I1 is a function of time, there will be an EMF induced in coil 2. So I call phi12 flux through coil 2 due to coil 1. And if I write Faraday's law, the induced EMF on coil 2, epsilon 2, will be equal to minus number of turns N2 in coil 2 d phi 12 dt. So phi 12 is the flux through coil 2 due to coil 1. And I'm going to call this minus M12, the mutual inductance, di1 dt. So this is the inductance created due to the time varying current in coil 1. So I define M12 as the mutual inductance. Okay, now what is this mutual inductance? Well, you can see that it is N2 times the flux phi12 divided by the current. So the mutual inductance M12 due to coil 1 and coil 2 is number of turns N2 flux on coil 2 due to coil 1 divided by the current on coil 1. So that is I1. Okay. Now similarly, if I have a time varying current on coil 2, this will create a magnetic field going through coil 1 and will induce an EMF. And therefore, I will see that the induced EMF on coil 1 will now be, using Faraday's law, minus the number of turns N1 d phi 21 flux on coil 1 due to coil 2 dt, which is minus M21 mutual inductance di2 dt. So we can see that mutual inductance on coil 1 due to coil 2 is basically N1, number of turns in the first coil, flux on coil 1 due to coil 2, phi 21, divided by the current on coil 2. Okay, so the EMF induced in one coil is proportional to the rate at which the current in the other coil is changing, and this creates a mutual inductance for the two coils. So M12 is N2 phi12 divided by I1, M21 is N1 phi21 divided by I2. Alright, so we considered a situation where we have two coils nearby. First, I set the current on coil 2 to 0, and I have a time varying current on coil 1. So the current is coming out of the page here, going into the page here, creating a magnetic field pattern as shown in this figure, and these field lines are going through coil 2. Since they're time varying, according to Faraday's law, there will be an induced EMF on coil 2, epsilon 2, minus N2 d phi 1 2, the flux through coil 2 due to coil 1 dt. And this is minus, normally I would call this minus L di dt, but this is now due to this mutual inductance, so it's minus M12 di1 dt. It's proportional to the rate of change of current in the first coil. So M12 is the mutual inductance. If I consider the symmetric situation where coil 1 current is set to 0, coil 2 has a time varying current, then I would have a minus N1 d phi 21 dt is equal to minus M21 di2 dt, and M21 would be N1 phi 21 divided by I2. So these two are the mutual inductances. The first one is due to coil 1 on coil 2, the second one is due to coil 2 on coil 1. So we can what it is telling us is that the EMF induced in one coil is proportional to rate at which the current in the other coil is changing.